So for reasons of safety, we might use a hand pump in order to do it. Additionally, having a second pump kind of provides for a means of isolation of equipment. If the piece of equipment won't operate with a power pump, but it will operate with a hand pump, you know that that item, some of the common parts of that circuit that make the hand pump make that item work are good. So it kind of rules out maybe some of the components that might be part of a problem in troubleshooting. Some aircraft use hand pumps also for reservoir servicing. You saw it from the video last week in Boeing aircraft and also in Airbus aircraft as well. You can service a reservoir via a dip tube that they put into a container of hydraulic fluid, and the way that it gets in the reservoir is via an onboard hand pump in the servicing bay. And lastly, for auxiliary use, if you want to use it for any other purpose that you might find necessary, there's at least a couple of different aircraft that have multiple functions for a hand pump aboard the aircraft, and we'll kind of talk about them in a bit. Additionally, hand pumps can be used for emergency use. In a lot of older aircraft, the method of deployment of actuators or actuator movement was via either an electrical pump or maybe an engine-driven pump. But if that pump should fail, the hand pump is a standby pump for emergency purposes. So again, just one reason we might want to have it aboard an airplane. Hand pumps can be classified as either single-acting or double-acting. What we mean by the term single-acting, does the pump produce flow on only one stroke of two? If the pump is double-acting, it'll provide flow on both strokes or for a complete cycle. So for most aircraft anyway, we'll choose to use double-acting pumps or double-acting hand pumps because they're much more efficient. You get flow on both strokes, so the amount of time required to make something work is halved in many cases by using a double-acting pump. Single-acting pumps do have a place, but not necessarily in aircraft. An example of a single-acting pump might be used for bulk fluid transfer of maybe oil or something on the ground, but not necessarily in an aircraft itself. If you want to think of it also, the single-acting pump, a lot of brake systems, if you break it down into their elemental components, are really single-acting type pump. The master cylinder is really a single-acting type of pump. So anyway, for most aircraft applications, double-acting is the way to go. There's a couple of different styles of double-acting hand pumps that might be used. The most common is called a piston rod displacement. That's the type of hand pump we have in the shop that we use for the checkouts. There's another type of double-acting pump that's called a piston displacement. That one uses a kind of a complicated arrangement of check valves and kind of a strange piston in order to make it work. But it's seldom found today. The reason being, I think there's too many working parts in that pump, and most of the pumps pretty much evolved into the usage anyway would be piston rod types. And then lastly, there are some aircraft that sport rotary pumps. Some of the C-130 aircraft, they have a method of replenishing the reservoir via an onboard rotary pump. Not all C-130s have it, but in the past they did. I think there's a picture someplace in the PowerPoint presentation or in your airframe book showing you a rotary pump. But this is what we're talking about. The styles of hand pumps kind of vary. If you look at the hand pump at the upper left, that's an example of a single-acting hand pump. When you pull the hand pump handle back, what you're doing is you're creating a difference in pressure across one of the check valves. The line that they label as with the arrow coming into it is the arrow from the reservoir. So as we pull the hand pump handle back, we're going to create a low pressure area on this side of the piston. So you pull the hand pump handle back, the check valve opens as we create a difference in pressure between these 2 points, and the cavity will fill with fluid. As you push the hand pump handle back, in this case to the left, what would happen then is the check valve shuts here, and as you might imagine, the check valve at this point will open and dispense fluid into the discharge line. So it's considered to be a single-acting hand pump. When you pull the hand pump handle back the other way, the chamber refills with fluid. You push the hand pump handle inboard again, the fluid is displaced out to the discharge line. So it's considered to be single-acting. you only have one flow stroke for every 2 strokes of handle movement. Do you all kind of see that? Okay. There's another type of hand pump, and we'll talk about this a little bit more in detail. This is a piston style, piston displacement hand pump. This one is in fact double acting. If you want to see the application of this type of pump, the hoist that we have in the south end of the building is equipped with this type of pump. We know that it's double acting because when we push the hand pump handle in either direction, fluid is discharged out of the outport line. And the way it kind of works is very interesting. They don't show it in detail very well, but in actuality, 2 of the check valves are incorporated inside of the piston, and 2 of the check valves are in the housing itself. I'll provide you with much more of a detailed view of maybe how that works in a little bit. Lastly, more commonly, what we find for aircraft usage is going to be a piston rod style of hand pump. This one is double acting. You get flow on both strokes with a hand pump. And in an actual application, it really only contains 2 check valves. One check valve is located at the inlet of the hand pump that's attached to the reservoir. There's another check valve that's internal to the piston. The airframe manufacturer may install a 3rd check valve that's at the discharge of the pump, but it's really upon the airframe manufacturer to install it there. I'll describe in detail why that's kind of necessary with this particular style of hand pump in a bit. This is an application of an aircraft that uses many different functions for the hand pump. So in this case, they've got a selector that the crew can manipulate in order to direct flow from the hand pump for a lot of things. In the Albatross, it's a amphibious aircraft. They can use it for both emergency brakes, and they can use it as a parking brake as well. So we can trap fluid in the brake actuator for parking purposes. We can also use it in the event that we need to supply fluid for emergency purposes to stop the aircraft. It can be used for deployment of flaps. I think they use single-acting actuators. So when you flip the selector to the flaps position, you can lower the flaps down. If you want to raise the flaps, I think you just put the selector back to the off position, and then a spring on the actuator, I think, drives the flaps back up again. Additionally, you can use it for gear down. It's an amphibious aircraft, so if we want to land on earth or on ground, we can lower the gear. And when we're going to be landing with floats, we can raise the gear up in order to make a water landing. There's this particular selector position on that for the hand pump for the off position. More often than not, when you see that used with a selector valve, what it does is it connects the discharge port of the pump, usually back to a vent line that goes overboard. And what that does is it prevents any trapped fluid that might be in the line from expanding as a result of thermal energy. So it dumps it overboard. Most of the hand pumps for aircraft are usually stowed in a location where they're accessible by the crew for this type of purpose anyway. Sometimes they may have a socket that the handle goes into, and the handle is kind of held separately. Here's what that Grumman looked like with the landing gear deployed. And again, it's an amphibious aircraft, and if you have to deploy the gear, you can actually use the hand pump in order to lower the gear down, and it raise it as well. Other aircraft use a hand pump maybe for just a dedicated purpose, and that's probably more common. This is from a Saab 340, and it uses the hand pump for emergency gear extension. There's a lot of other ways that we can lower the gear down for emergency purposes, but this aircraft has got a hand pump handle stowed near a socket beneath a cover in the cockpit, and it allows you to manipulate the gear down in the event of you can't get the gear down by normal methods. Here's an example of a hand pump that's used in a Chinook, Boeing Vertol Chinook, and you can see what they've done. You got the hand pump mounted in the aft section of the aircraft. It's primarily for utility purposes. We can use it maybe to open and close the cargo door, the ramp assembly that's on the door on the aft end of the aircraft. Additionally, that hand pump might be used to maybe charge an accumulator with hydraulic fluid. So they can be used for a lot of purposes, but again, this would probably be for a usage where we want to manipulate the cargo door open and closed, or possibly replenish an accumulator with fluid that's been discharged for whatever reason. So we can use it for that. And here's that picture of the rotary hand pump. Some versions of the C-130, I understand, used a rotary hand pump aboard the aircraft. It's probably got vanes in it, kind of like a wobble pump. And the idea is you turn the hand crank in order to develop flow. So there might be a tube assembly attached to it, and what you can do is you can service a reservoir maybe, just like you did with a Boeing style of pump aboard their aircraft. A single acting pump, well, again, what does that mean? It means that you have flow on one, and only if on a complete cycle of operation, handle in and handle out, you only have flow on one of the two strokes. So you can see what they have inside of the pump. They've usually got two check valves, and the fluid is going to be filling the cavity that's on the left side of the piston. When you pull the hand pump handle back, the cavity fills with fluid because we create a difference in pressure between 2 points. As you pull the hand pump handle back, a low pressure area is developed on this side of the piston, and the fluid under atmospheric air pressure in the reservoir is able to fill that cavity or fill that void up. So that's fine. When you push the hand pump handle forward, the check valve that they label as A will close, and the fluid will be displaced out of check valve B into the pressure manifold. If you want to make the hand pump operate again, you have to fill it back up. So what do? You pull the hand pump handle back one more time. The cavity fills with fluid, and then as you push the hand pump handle forward, the fluid is displaced out. Okay. So single acting, not too efficient, but again, used for bulk fluid transfer, maybe in for ground use, but not necessarily for airplanes. Double acting, this is a double acting piston rod style. I've got a better view of how this thing kind of works, and I brought the cutaway in the shop. More often than not, these pumps contain two check valves in them. One check valve will be located at the inlet of the pump. This is the port that connects to the reservoir. A second check valve is incorporated inside of the piston assembly. As the name implies, double acting. It means that for every stroke of the hand pump handle, fluid is being displaced out of it. Much more efficient in operation. It works because of a difference in volume on each side of the piston. The rod occupies some of the volume of one side versus the other. It's just not a flat piston face. It's true that we find that on one side of it, but the other side of the piston face is attached to it as a rod that occupies some of the volume on that portion of the cavity. So let's kind of take a look and see how this thing kind of works. Let me see if I got a picture up here for you. The top picture shows you that what would happen is if you were pulling the hand pump handle back, what's happening is two simultaneous things, two things occurring at the same time. What you're first doing is you're allowing one check valve at the inlet of the hand pump to open. And again, the reservoir would be connected to the inlet part of the pump. We're creating a low pressure in this cavity, and that's what's really allowing the check valve to open and allow the cavity to fill with hydraulic fluid from the reservoir. At the same time, there's a check valve that's inside of the piston. That check valve is seated, and whatever fluid is trapped on this side of the piston is being forced out the outlet, because as you pull the handle back, this chamber is diminishing in size. And as you know, liquid is considered to be incompressible, so the liquid has got to be pushed out into the pressure manifold. So the cavity fills on this side with fluid from the reservoir. Simultaneously, the fluid that's on this side of the cavity is discharged or displaced into the pressure manifold. So that's one of the strokes in operation. The in-port check valve is unseated, and the out-port check valve is seated. By the way, too, the FAA sometimes uses strange verbiage in their exams. When they're talking about the in-port check valve, they're talking about the inlet check valve. The out-port check valve, even though it's not technically mounted at the outlet, it's exposed to the outlet side of the pump. So the check valve that's inside of the piston is really the out-port check valve. Okay, so we displace fluid, pulling the hand pump handle back or extending it. Let's push the hand pump handle back in and see what happens. Well, as you push the hand pump handle back in, realize that the cavity on this side of the piston is not the same size as what you had over here. The rod occupied some of the volume on this side. So the fluid that was normally on this part of the cavity, not all of it can fit. As you push the hand pump handle inboard, whatever fluid was here, obviously not all of it can fit on this side of the piston, because the rod occupies some of that volume. The difference in volume has to be pushed out the outlet of the pump. Does everybody kind of see that? Yes or no?
Yeah.
Okay, all right. So notice also what's happening with the check valves is the reverse of what happened during pulling the hand pump handle out. The check valve at the inlet of the pump is now seated, and the discharge, or I should say the outlet of the outlet check valve is now open. So what we're doing is we're really transferring fluid from one chamber to the other, but again, not all of the fluid can fit because again, this cavity, when the piston was pulled all the way back, was fairly large, but as you push the hand pump handle in, the rod occupies some of that volume, so the difference in volume has to be pushed out of the hand pump. All right. So we still produce flow on both strokes though, is that not true? The answer is yes. So as you pull the hand pump handle back, fluid is pushed out. As you push the hand pump handle back in, fluid is still pushed out.
But a double acting pump ever as efficient as this, as a single stroke of a?
No. I don't think you can make it as such. I mean, the whole idea is to be able to pump out, a quantity of fluid that would be in a short period of time. I guess if you're defining efficiency that way,
Yeah.
really you can't do it any other way. Yeah.
I'm just confused. Sorry, I'm just confused about how that's the ball, the unseated part, like why it doesn't do the opposite. Because if you pull on the pump and the pressure would go out this way on the top one.
You're creating more pressure over here than what you have at the discharge side. So the ball is forced open, filling the cavity up. You have to produce more pressure, if you want to think of it that, than what you have at the outlet of the pump.
Okay, that makes sense.
Okay, all right. So, okay, fine, everything works groovy, right? Okay, so piston rod displacement hand pump. Now, here's kind of the interesting thing. Many airframe manufacturers will install a third check valve. As the illustration kind of erroneously illustrates, they sometimes do not incorporate it right at the outlet of the pump. It'll be installed in a line that connects to the outlet though. So it forms kind of a chamber that we have external to the pump, but the actual placement, it isn't right at the outlet. It's usually installed by the airframe manufacturer in the pressure manifold at the outlet point. Now, what's the importance of that third check valve? Well, let's take a look back at this other picture and kind of take a look and see why it's important. Let's assume we have a failure. Let's assume that the check valve at the inlet has failed open. Maybe the spring is broken, maybe the ball is cracked, whatever has happened, but the check valve is now stuck open. You know that liquid takes the path of least resistance, right? Okay, so here's the cutaway hand pump. I'm going to pull the check valve down. You allow this cavity to fill with fluid over here from the reservoir, but as I push the handle back in, the check valve that's inside of the piston won't open because there's an easier path for this fluid to go back where? Back to the reservoir. So all you're doing with a failed check valve at the inlet is you're sending fluid in and out of the hand pump. You're never able to transfer it to the discharge side. Does everybody kind of see that? Yes or no? Yes. Okay. Now let's take another view. Let's talk about the check valve that's inside of the hand pump. This is the one inside of the piston. If that check valve fails open, you're doing the same thing on the discharge side of the system in the pressure manifold. All you're doing is exchanging fluid back and forth between these two cavities. You're never able to trap it at any given time in order to push the fluid out and keep it out. Does everybody kind of see that? So what I would tell you is this: if you have a failure of either check valve inside of the pump, the hand pump is completely inoperative. It will not work. So what do we do to remedy that? We install a third check valve. We put the third check valve in the pressure manifold so that it'll prevent any particular check valve, if in fact it should fail, from producing complete failure of the hand pump. If we've got the third check valve installed and the check valve at the inlet should fail open, the hand pump will convert itself into a single acting hand pump. When we draw the hand pump handle back, fluid will enter into this cavity. But that third check valve acts as a blocking check valve that prevents system pressure from allowing the transfer of fluid back into this cavity onto the other side of it. So as you pull the hand pump handle out, you will in fact be displacing fluid coming out of the hand pump. But when you push the hand pump handle back in again, this side of the cavity will fill with fluid, so it's really turned the hand pump into a single acting hand pump. The same thing is true if the check valve inside of the piston fails. The hand pump will work, but it will only work on the other stroke. In other words, when you push the hand pump handle in, that third check valve, the safety check valve, prevents system pressure from acting internally on the piston, and it allows that cavity to displace fluid, so fluid will come out of the hand pump. But again, without that third check valve installed, hand pump is not going to work. By the way, too, if that third check valve fails open, you'll never know it because, again, hopefully the other two check valves will, in fact, protect the circuit so it will work. But anyway, that's the idea of the third check valve that we have inside of the pump. Okay, so safety check valve. A little bit on troubleshooting. The FAA has got a few questions involving troubleshooting hand pumps for aircraft. And all they really talk about are just what we talked about, the piston rod displacement hand pump. Forget about the third check valve for just a bit. And let's assume that all of a sudden you've got the hand pump handle inboard, and all of a sudden one day the hand pump handle just kind of kicks itself out toward you. What might be wrong? It might be possible that the system pressure is working on the piston check valve, and it's allowing the piston to be force itself out. So what's happening is this: you've got the internal check valve that sticks open. The fluid under system pressure finds the larger of the two surface areas and allows the piston to be pushed all the way back. So that's why it happens. Now, if it's a slow leak, or maybe the piston is leaking, it's going to creep. But nevertheless, the idea is, again, the fluid is acting against the larger of the two surface areas. So therefore, that's why the handle pops itself out for severe kickback. You can push the handle back in, but as soon as you let go, again, system pressure pushes the handle back out, simply because we've got more surface area on one side of the piston. Handle creeps out, same deal. Either the check valve is slightly leaking or the piston seal is leaking on itself. If you can't push the handle forward, particularly after overhaul, well, you know that liquids are considered to be incompressible. It's possible that that check valve that's inside of the piston has been turned backwards so that you can't transfer fluid from one side to the other. So I think the FAA has got at least one test question for you. If you can't move the handle in the direction, the inboard direction, the possibility might be, if the pump has been recently overhauled, someone may have reversed the position of the piston check valve. And simply what's happening is you can't compress a liquid. So the fluid that's in this chamber forward of the piston can't be transferred to the other side of it. So that's a possibility. Okay. Next up, just a little picture to kind of show you what we have. This is from a military aircraft. I don't know specifically which one. The hand pump draws fluid from an emergency reservoir, not necessarily from the primary reservoir. But in many aircraft, I think we talked about previously, maybe last week, the plumbing of the hand pump for a lot of reservoirs is by a port that's connected to just one reservoir. For many aircraft, if we have a reservoir that kind of looks like this, we have a standpipe in the reservoir, and then we just got the outlet at the bottom of the reservoir, like that. The standpipe usually connects to the power pump, and the hand pump connects to near the very bottom of the reservoir. And remember what I told you too, for a reservoir, the primary function of the standpipe is to prevent contamination from getting into the power pump. But the secondary purpose is to provide for segregation of hydraulic fluid so that the hand pump will continue to function if the level drops below the standpipe. Does everybody see that? Yes or no?
Yes.
Yes, okay. Okay. This is the other style of pump. It's called a piston displacement. I got this out of an old book, and I was looking around in the shop trying to figure out where one existed. And the hoist does in fact have this particular pump in it. It uses a waist type of piston assembly. 2 check valves are inside of the piston, and 2 check valves are inside of the cap or the end of the housing of the hand pump. and there's a ball socket that's attached to the handle. When you rotate the handle in one position, you cause the piston to be pushed one way. When you rotate the handle in the opposite position, it forces the piston in the other direction. In either direction of operation, two of the check valves will open, and if you push the hand pump handle back the other way, the alternate set of check valves will open. So let's push the hand pump handle this way to the, we'll call that to the left. What that does is it forces the piston, in this case, to the right. What happens then is the check valve that's inside of the piston will stay closed. The check valve that's inside of the cap assembly or the housing opens, and we deliver fluid out this port that goes into the pressure manifold. At the same time that that's happening, you're creating a low pressure on this side of it because the cavity is getting bigger. The fluid from the reservoir enters into this cavity and fills the cavity up. Okay? So if we push the hand pump handle back the other way, you can see what happens. The fluid that's on this cavity cannot be compressed. The check valve inside of the piston will seat. The check valve that's inside of the housing opens and displaces fluid. At the same time that that's happening, the fluid from the reservoir fills the void on this side of the piston and provides for fluid for the next stroke in operation. So it's a little bit different than the the piston rod displacement hand pump. It's got double the number of check valves. You're probably not going to see it in too many aircraft, but nevertheless, they do in fact exist. Don't know about any safety features for them, but again, it's kind of an antiquated design. The only difference that I can think of between this and the piston rod, it allows fluid to enter the pump on both strokes. The piston rod displacement hand pump, although it's double acting, that pump only allows fluid to enter into it on one of the two strokes. In this stroke, if you call this the extension stroke, fluid enters the pump. But notice what's happening during the other stroke. The inlet port from the reservoir is closed. Okay, so it's a little bit different. Okay, all right. An example of maybe a utility hand pump. This is on an Airbus aircraft. It says on single-aisle Airbus aircraft, there are two hydraulic hand pumps. Normally, an electrical pump operates the forward and aft cargo doors, but if there's no electrical power or if that pump fails, these pumps provide backup. More precisely, one pump provides the backup. It is used to manual charge the yellow hydraulic system and operates the doors. The other is used to manually fill the reservoir of the three hydraulic systems, yellow, blue, and green and blue. Pumps are installed in unpressurized belly fairing of the aircraft, one on each side just behind the main landing gear. So again, these aren't for emergency purposes. This would be for utility use in the aircraft. One for reservoir servicing, the other to open a cargo door. A little bit about overhaul of hand pumps. What I can tell you is this. There's a schematic, or at least a pictorial that they give you in your Merrill Fluid Power Book that looks like this. It shows you a hand pump bench test setup for checking a hand pump for operation or serviceability after overhaul. And what it requires is a source of fluid for use in the hand pump. It requires a shutoff valve. It requires the connections to it, and also a pressure gauge that's been keyed into the discharge port. So there's two different kinds of tests that we do. We do a leakage check, and we also do a pressure check of the pump. No two pumps are exactly the same in terms of what the requirement is, but what I can tell you, this is just kind of a general overview of what some of them provide for both a bench check for pressure and leakage, and this is what they do. They'll use the hand pump with the valve shut that they use for testing, and what they want to do is obtain what they call proof pressure test, or proof pressure. It's usually 1.5 times whatever normal system pressure would be. So, okay, that's one thing. You shouldn't have any leaks doing that test. So you have to test it both in the extended and retracted positions, and it has to hold pressure for somewhere between 2 to 5 minutes. There's another test that they call a leakage test, and I guess we're just kind of checking the integrity of the internal components for leaks. Normal system pressure is obtained for 2 minutes, and with the piston in an intermediate position, there shouldn't be any piston creep either way. Maximum pressure drop should be somewhere between 50 to 100 psi and held for about 2 minutes. By the way, too, if someone were to ask you about the overhaul of a hand pump, the overhaul of a hand pump by FAA regulations is not really defined. If you look in FAR 43 Appendix A, they will tell you that overhaul of powered fuel, oil, and hydraulic pumps are considered to be major repairs for return to service. However, omitted from that would be hand pumps. But if it's engine driven or electrical, yeah, we know in fact that it's going to be a major repair for its return to service. But by its omission in Part 43 Appendix A, what does that mean? It means you as an airframe mechanic may in fact overhaul a hand pump, even if it's an emergency hand pump, provided you abide by the recommendations or the overhaul instructions, and you furnish a logbook entry in the logbook as such. So again, you in fact as an airframe mechanic can do it. It doesn't require or necessitate executing FAA Form 337. So again, by its omission from Part 43, considered to be not to be a minor repair, not major. All right. Some thoughts about hand pumps that I can give you. Understand because of their position in the hydraulic system, they're usually plumbed to the very bottom of the reservoir, so they're sometimes prone to contamination. You might want to think about that if you're using a hand pump and verifying the emergency system for maybe an extension of gear. Before you do a gear check and you want to verify that that works, make sure that the fluid in the reservoir is clean. Very seldom do they have anything that obstructs the hand pump inlet from the reservoir for reasons of safety. But again, from experience anyway, the fluid in many reservoirs is really dirty down at the bottom. So verify that the fluid is clean before you use the hand pump. If you see a selector valve that's used for multiple functions with a hand pump, you can use that for troubleshooting purposes. Again, because the hand pump is just a source of flow, you can sometimes verify certain portions of the circuit work or don't. And again, because there's some commonality among all the components in the same circuit. I'll give you an example of some of that when we get into troubleshooting later, but you should know that, well, I'll give you an example. Let's say we had a reservoir with a power pump and a hand pump, and we had a flap, and the engine-driven pump won't function to make the maybe the flap operate, but the hand pump will. Is there something wrong? Well, maybe, but I know that the flap in fact works, but maybe the first thing to check for troubleshooting might be the level in the reservoir. Because again, if the hand pump makes the flap work, but the landing gear or the engine-driven pump doesn't, it may be as simple as just replenishing fluid in the reservoir and things are back to normal again. So kind of one of the key things in troubleshooting. One other thing too, the selector valve that's used, it may vent the pump discharge by intention, usually to a drain line, and it prevents the fluid from thermally expanding or being trapped. So that's why they have them. And that's it. So what questions do you have on hand pumps? Questions?
Oh, I have one.
Yeah.
What kind of fluid is used in it?
Depends on the system. I mean, we have hand pumps, whatever seals would be appropriate for the fluid, that would be the type of fluid that we're using. If we're using like 5606 in a hydraulic system, many of these pumps are commonly fitted with seals that are for 5606. Oh, one other thing too. The way that they're rated. If you look at the product literature for a hand pump, they're rated in displacement per cycle. A cycle, again, is defined as both strokes. So maybe you've got 3/4 of a cubic inch on each side that's displaced, or at least 3/4 on one side and maybe a half cubic inch on the other. The total combination of the two displacements really gives you the total displacement for the hand pump. So displacement per cycle. Also, sometimes you'll see ratings that are applied to hand pumps in product literature. This is a reference to their ability to withstand discharge pressure. In other words, how much pressure at the discharge port can we have and the pump not leak. So you might see something like a rating of 1,500 PSI or 3,000 PSI. So that refers to the pump's ability to withstand leakage when that pressure is applied to the discharge port. So against that rated pressure. Okay, all right, so much for hand pumps. Next, let's talk a little bit about accumulators for aircraft. And let's kind of get there. Okay, we're going to talk about these devices, accumulators. We briefly talked about them when we talked about open center and closed center hydraulic systems, but they're important, especially in closed center hydraulic systems. Remember, in a closed center hydraulic system, you're building and holding hydraulic pressure. With the theory is this though, for the system to function normally, you have to be able to build and hold hydraulic pressure all the time. If you sustain any type of leak in a closed center hydraulic system, there goes the pressure and there goes your ability to operate any piece of equipment. All it would take is a pinhole leak someplace in the circuit, or maybe an internal leak that allows system pressure to escape and go back to the reservoir. So if you can't hold pressure, well, the system isn't going to work very well. So one thing that will kind of help us is an accumulator in a closed center hydraulic system. The purpose of it is to maintain system pressure in the pressure manifold. It has a lot of different functions depending upon the aircraft style and type, and you may find multiple of them used in different subsystems of the aircraft hydraulic system. There's usually an accumulator, a gas charge that we put in it that we call a precharge. That provides the push of the hydraulic fluid out of the accumulator. And we'll talk about how that kind of works in a little bit. You can see where it's mounted. Here you've got the reservoir, you've got an engine-driven pump, you've got what's called an unloading valve or a pressure regulator, and then immediately after that we have the accumulator. And we're building pressure in this line called the pressure manifold. When the pump is pushing out fluid, what it will do is the fluid will enter into the accumulator and further compress the gas charge that you put into the accumulator, and we will see a buildup of system pressure on the gauge. So again, it's a device to kind of hold system pressure. Some cases, in some books, I'll refer to an accumulator as a pressure reservoir. So if you read some of these really old books, well, it's a kind of a reservoir, yeah, but again, it holds fluid under system pressure. So again, that's why they use the term pressure reservoir. The functions of an accumulator. It supplements the pump under peak loads. Well, you can see here that the primary source of fluid flow is going to be the engine-driven pump. But let's say we had many actuators that were in the circuit, not just the two that you see here. You operate so many of them at any given time, you can't keep up with the flow requirement for all of those actuators to move simultaneously. Well, the accumulator works kind of like a battery. Not only do we deliver flow out of the pump, but for a short period of time, any stored fluid that might be of value to us that was in the accumulator could be used to help move those actuators. So it supplements the pump under peak loads. Another thing that it does, one more thing, it limited emergency operation if the power pump fails. Let's assume that we're flying along, we've already got the gas charge in the accumulator, and the accumulator is charged with fluid as well, so the bladder or the diaphragm has been displaced and pushed down. All of a sudden, the shear shaft on the pump fails. For a limited period of time anyway, you've still got the push on the fluid because the gas pressure on this side of the accumulator is attempting to push the fluid out. So at least until we've pushed the member up as far as it can go and pushed all the fluid out, you have some opportunity to operate these actuators that we have on the circuit. Okay, so provides for limited operation if our engine-driven pump should fail. Okay, so it does that. Another thing that it does, let's see what we have. Prevents rapid pressure loss from hydraulic fluid leakage. I try to point this out during the checkout in the lab when we do the accumulator. All it takes is a tiny little leak in the circuit, and without the accumulator in the circuit itself, the system pressure will drop itself off to zero. We've got a valve that's on the mock-up board. It's just a hand-operated wheel valve that we can cut off the hydraulic pressure that was normally supplied by the accumulator. As soon as you shut the valve off, you can see that the line pressure drops. Let's assume that the valve is right here. We shut that fluid off, and or put the shut-off valve right here. The gauge will drop itself off to 0. The problem is you've just got all it takes is a tiny little pinhole leak any place in the circuit, and the pressure will drop itself off. Remember that pressure comes as a result of confinement of hydraulic fluid. If you can't trap the fluid, you can't build and hold pressure. So, okay, you open the valve back up again, that little hand wheel valve, and all of a sudden the pressure comes back again. Magic? No. What's happening is you've just got the pushes back been supplied back to onto the fluid. So without it, you're dead in the water if you've just got a minute leak. I defy any hydraulic system to be 100% leak-free. It's impossible. So without it, you know, a manufacturer couldn't really have a functioning hydraulic system. You're going to have a drop of hydraulic fluid that's going to find a way out no matter what. Since it's a closed-centered system, the system is already under pressure anyway. So again, all it takes is just a small leak and the pressure goes to 0. What makes matters even worse is this. Let's assume that that leak is not an external leak. Let's assume that maybe this relief valve is leaking internally, or the selector valve is leaking internally. The fluid in that case isn't coming out of it, it's going back to the reservoir as the leak goes on. So the fluid flow goes through the relief valve and the system pressure drops. So again, what's happening is the accumulator is kind of replenishing the loss from leakage. Okay, so it's a good thing. So that's why we need it. Also too, dampens pressure surges. If you've ever been in an old house, I remember my grandparents had this old rickety shack back in Chicago. Every time you turn the water tap off in the lavatory, you heard this loud hammering or banging action. And the reason was is they didn't have an air trap in their in the water line. So what the accumulator does, it kind of performs the same kind of function. The instant that you shut off a selector valve, the stoppage of hydraulic flow just ceases immediately, and it produces kind of a shock wave throughout the circuit. What happens at the accumulator, the gas charge gives a little bit, and maybe the diaphragm or the bladder kind of sways or moves a bit in order to accommodate that surge. So what it does is it dampens pressure surges from the sudden stoppage of hydraulic fluid flow. And again, it's damaging to the hydraulic system because it does put a stress on it if it occurs. So again, that's why it's there. So it dampens pressure surges. Another thing that it does, let's see what else it does. One more thing, it provides for thermal expansion of fluid. When you've got the selector valves all in the closed position, as you see here, if a source of thermal energy is exposed to that fluid that's in these lines in the pressure manifold, you know what happens. The fluid is going to try to expand. If there's no give in the system for expansion, you're going to burst a line. So the accumulator, with its gas charge beneath it, the bladder or the diaphragm that you have inside of it will give a little bit. The gas inside of the bottom chamber compresses a bit, but we've got that space now available for that fluid that's under expansion. Even with, I don't know if Lyle has talked to you in the landing gear class, with a lot of the shimmy dampers for aircraft, some of the shimmy dampers also have a provision for thermal expansion in them. When the fluid gets hot, there has to be a way for the fluid to get out. So same thing with a lot of independent brake systems. They've got a compensator in a lot of independent brake system master cylinders. The compensator stays open when your foot is off the brake pedal for that reason. So there's a way for the fluid to get out of the brake line and back to the reservoir section. Well, we can't do that with the pressure manifold, but what we can do is we can provide for additional space by allowing a little bit of give, because the gas side of the accumulator will compress a bit in order to allow more volume for fluid on this side. Do you all kind of see that? Okay, all right. So, okay. Provides for thermal expansion of fluid. And lastly, holds the regulator unloading valve in the open position. Well, The unloading valve is kind of critical in the circuit. It's kind of an on-off switch, but once we've built up system pressure to a particular point, the unloading valve will deliver flow from the pump back to the reservoir unrestricted. So when we use components in the circuit, the pressure drops off. The unloading valve then allows more flow to build into the circuit to establish pressure, and then shuts itself back off again. So the unloading valve is kind of like a pressure, a voltage regulator in an electrical circuit. And again, it's kind of an on-off switch. It regulates the pressure and flow in the, or mostly pressure in this particular case, into the pressure manifold. You can see what happens also in an electrical circuit if you don't have a battery installed with a voltage regulator. If the voltage regulator doesn't know what to do, you know, it won't stay in the one position long enough so that it'll keep itself stable. So eventually the contacts wear themselves out, vibrating from one point to the other. So we need the accumulator in order to hold the unloading valve in what we call the kicked out position. So once we establish fluid in the line under pressure, what we want to do is we want to hold the unloading valve in the kicked out position so that any additional flow from the pump goes back to the reservoir. Only when we start to deplete the accumulator of fluid past a certain point do we want the unloading valve to open back up again, or at least provide flow back into the circuit to reestablish pressure. So the idea is to hold this thing in the open position as long as possible to prevent wear and tear on this component. There are mechanical components inside of this thing that will beat themselves to death if they don't stay in the kicked out position for a long enough period of time. The thing goes from kicking to kick out, kicking to kick out, kicking to kick out so fast that, again, it just wears it out. So this accumulator is working kind of like as a battery. You have to bleed off that voltage from that battery before the unloading valve says, okay, now we can deliver flow back from the pump into the circuit to build pressure. So it's kind of a necessary device. All right. So those are the functions of an accumulator. By the way, no particular function is a primary function. You may find several subsystems in a hydraulic circuit. You might find maybe a landing gear circuit that's hydraulic, maybe a flap system, maybe a brake system. They all may have an accumulator in their respective circuits, and none of them may be, or they may function for all different purposes. You don't know. But the airframe manufacturer specifies that they should be there for some reason. Some might be for thermal expansion, some might be to dampen pressure surges, some might be installed in the main pressure manifold in order to supplement the pump. And some of them don't have to be very big at all. If you look at some accumulators, they're tiny. And again, the only function to be certain is to control thermal expansion. So again, volume requirements are quite different and our usage is quite different in many aircraft. This shows you a kind of a simplified schematic of an older aircraft. This is a Convair 340 from the late 1940s, early 1950s. They're showing you an accumulator in the pressure manifold. So what we have is a system pressure that's on the top side of the accumulator. And then what we have on the bottom side of the accumulator, we've got a gas charge that we furnish that we call a pre-charge. So they've got an accumulator, they call it an air valve, but it's really a servicing valve. Notice also in the illustration, we've got a gauge that's been tied to the gas side of the accumulator. And then for indicating system pressure, they have a remote reading, they've got a gauge mounted also, but they have a remote method of indicating system pressure on the fluid side of the accumulator. This is kind of rare today. More often than not, you won't find a gauge mounted on the gas side of the accumulator. You'll find generally just a system pressure gauge. I'm going to show you after break the method that we use to determine the gas charge that's in the accumulator using the system pressure gauge. But we'll talk about that in a little bit. Also, too, there's a little bit of information that's somewhat misleading in your Merrill Fluid Power Book. They talk about a certain type of accumulator that's called a self-displacing accumulator. They tell you that it contains no air. Well, actually, it does have a vented chamber in it. We'll talk a little bit more how it actually works. But it's got 4 chambers. It's got a gas pressure chamber. It's got a system pressure chamber. It's got a vented chamber on the top, and it's got another chamber that works as a reservoir section. But I'll talk to you a little bit about it in a minute. When we finish up talking about the standard accumulators, we'll kind of get to that type. Let's talk about the 3 basic types of accumulators. One type of accumulator is called a diaphragm type accumulator. It's really made out of 2 hemispheres that have been screwed together, and what we have is a flexible rubber element between them that they call a diaphragm. One of the ports is called the fluid port. This goes into the pressure manifold. The other port is the service port, where a service valve has been installed. And it's actually very simple. If you look at many of them too, many of the diaphragm type accumulators have a metal screen that's furnished at the fluid port. The purpose of that metal screen is to prevent extrusion of the diaphragm. If there's nothing but gas pressure on this side of the diaphragm potentially could be pushed out of the fluid port and extruded. So the idea is that screen prevents that from happening. Another type of accumulator might be a bladder type accumulator. It's a single piece sphere with a bottom plug. What's inside of it is a device called a bladder, and usually mounted on the bladder is a metal disc. The metal disc is there for a reason, for the same reason that we had the metal screen mounted in the diaphragm accumulator. The purpose of the disc is to prevent extrusion of the bladder if nothing but gas pressure is on this side of the bladder. So it prevents it from being pushed out of the fluid port. Same idea, on the opposite side of the accumulator, you find a port for mounting a service valve. And that's all that you got. A third type of accumulator is called a piston type accumulator. This one is cylindrical, and it's usually got a piston in it that traverses both ends of the cylinder. One side of the piston has got gas pressure in it that we furnish, called a precharge. The other side of the piston will have system or fluid in it that we're trying to push out of it. In many of the piston type accumulators, a port or an orifice opening is provided. And what that port does, that is, it provides for a lubrication port to lubricate the 2 seals so that the piston can traverse back and forth inside of the cylinder. Same idea. We've got a service valve that's mounted on this side of the accumulator. The basic operation is really simple. The gas charge that we furnish into the accumulator is the force that forces the fluid out. It's also the force that has to be overcome by fluid trying to get back into the accumulator. So you can consider that gas charge to be a force that pushes the fluid out. It also has to be overcome as the fluid tries to re-enter into the accumulator. I've got a couple of other pictures too. Here's a few that I stole from the internet. I don't understand why they got this thing bolted with a zillion bolts, but the DC-3 only had like 800 or 900 PSI system pressure regulated in the circuit. But I don't know, maybe they were crazy. I have no idea. But in any event, they got this thing bolted with a zillion bolts together for a diaphragm accumulator. Another picture of this is a bladder type accumulator. Kind of show you how it works. And this is the inside, a picture showing the inside of the bladder of a bladder type accumulator. And they're showing you the metal disc that's attached to it to prevent extrusion of the bladder going out the fluid port. And a piston accumulator. Now, as far as mounting, something kind of interesting too. For the bladder and the diaphragm type accumulators, what we would prefer to do is we would prefer to mount the accumulators with the gas side facing at the 6 o'clock position. Functionally, those accumulators will work even if they were inverted. If I wanted to install the accumulator so that the gas side was up and the fluid side is down, that's fine as long as the fluid is plumbed into the pressure manifold. But there's a distinct advantage to having the gas side facing down. The reason is for troubleshooting purposes. If in fact we are checking for a leak of the bladder or the diaphragm, by having the service valve mounted at the 6 o'clock position. If we were to open the service valve up and we witness the presence of hydraulic fluid, that would indicate that we have a leak in the bladder or the diaphragm. Does everybody see that? Okay, so functionally it'll work, but if you install it with the gas side facing down, when it comes time to check the gas charge and you see fluid coming out of the gas port, the service valve, you've got a leak in the bladder or the diaphragm, all right? With the piston type accumulators, it doesn't really matter too much. However, the gas, again, you want to have maybe the gas side facing toward the down position so that if you open the service valve up and saw fluid coming out of it, well, okay, you got a leak someplace. But anyway, that's a piston accumulator. One thing that will render a piston accumulator non-functioning would be the cylinder being crushed or collapsed. So you have to kind of look at these things kind of carefully. If something has struck the cylinder, obviously the piston is going to be frozen in a particular spot. The accumulator won't work. So you have to be able to push on that fluid at all times. So again, if that can't occur, the accumulator is out of function. Different styles of them, piston accumulators with different capacities for the same reason. You have to support the system for whatever its needs might be. So you might find one for landing gear, you might find one for thermal expansion, you might find one for maybe a steering circuit in an aircraft. And lastly, let's talk a little bit about these self-displacing accumulators. Well, okay. I stole this picture from Moog, which is a manufacturer of a lot of hydraulic components, and they provided me with a picture that they furnished. But the self-displacing accumulator is kind of like a standard piston accumulator, but it's been modified. Rather than just have two chambers in it, a fluid chamber and a gas pressure chamber, it contains four. It's got a gas pressure chamber, usually serviced with nitrogen. It's got a high pressure fluid chamber. It's got a low pressure fluid chamber, kind of like a reservoir, and it's got a vented chamber. If you want to look at it in cross section, here's a picture of one from a H60 showing you the two extreme positions of a piston. This would show you what you would have with the accumulator charged with hydraulic fluid under the gas pressure that has been compressed more than what you put into it. So what happens is the system pressure comes into this cavity, fills it up, and compresses the gas charge, so the piston has been pushed all the way over to the left. The cavity on this side of the piston has been pretty much been emptied, and that's going to be our return port that would form kind of a reservoir section later. The reason that they use a lot of self-displacing accumulators is because they didn't have enough space for a standard reservoir. Do they have a reservoir in the aircraft? The answer is yes, but it sometimes doesn't provide enough capacity. So what this chamber that they have on this side of the piston will provide for eventually, it'll provide for additional storage space of fluid that is technically unpressurized. So when the piston finally moves over, the displaced fluid from an actuator will fill that cavity. On the H60, if you want to start the aircraft, you push a button in order to release fluid from the accumulator. So what happens is the fluid in this accumulator is pushed out. It goes to a hydraulic motor, which motors an APU, an auxiliary power unit, and that ultimately will start the gas turbine engine. But we have to provide a source of hydraulic fluid to the motor to get it running first. So we push the fluid out of here, and it goes to the hydraulic motor, starts the APU, that's supplies compressed air to start the T700, and then the aircraft starts. Okay, well, you realize that fluid is incompressible. There was fluid that we're pushing out of this thing. There has to be some return fluid from that motor. Well, as the motor spins, the fluid that's coming out of the motor, hydraulic motor, returns back into the return manifold and now occupies this cavity. So you can see what happens is the piston is moved to the right, the fluid is being displaced into the motor, the recovered fluid from the motor enters back into this part of the piston and now occupies that cavity. The aircraft finally starts, the hydraulic system begins to pressurize. Eventually, the piston will be then pushed back to the plate where we started again. Does everybody kind of see that? Okay, so that's why they call it self-displacing. So again, the fluid that comes out of it is the fluid that came back into it. So an interesting device. The way that they kind of monitor the condition of the accumulator is with a tape reel type of indicator that they have on the accumulator. Obviously, the piston position has a direct bearing upon the fluid that's contained inside of the pressurized cavity. So we can tell at least the piston position by viewing the indicator when we want it to. When we want to. Okay, so that's a self-displacing accumulator. Here's another kind of picture showing you the same thing, kind of a generic view of it. But again, sometimes manufacturers, they have to have additional storage space for fluid that's not pressurized. So they provide this additional cavity with a kind of an H-shaped piston, and the piston just kind of goes back and forth between the two different positions in order to accommodate fluid. Here's one in a Chinook aircraft, and you can use the hand pump, I think, in the Chinook in order to replenish the accumulator. This is a common feature also in a lot of Sikorsky aircraft. Sikorsky and some of the other helicopter manufacturers opt to start hydraulically. And there is a big advantage in doing something like that. If you use electricity with an electric motor to try to motor a gas turbine engine, sometimes it's really hard on the starting system, particularly a battery. If you're using a NiCad battery, it can lead to thermal runaway, and you can easily deplete the battery if you're not careful. So what Sikorsky has done for most of its military aircraft, they provide a method of starting hydraulically. So they use the accumulator. The accumulator is charged with fluid from the previous flight, and it's held in reserve for use when you want to start back up again. So again, okay, you will start the aircraft up, you release fluid into the APU motor rotates, APU starts, gas turbine eventually can start from that. What happens though when you displace all of the fluid out of the accumulator? Well, you've got the hand pump. So the hand pump is one method of forcing the fluid that's been discharged to make the APU start. So if your APU doesn't start, well, okay, we can at least charge the accumulator back up again and provide a restart attempt. Some of the Blackhawks too, they're furnished with 2 accumulators. There's a kit that can be furnished on some of the Blackhawks. They call it a winterization kit. It uses 2 accumulators in parallel with each other. And the reason they do that is in cold weather, sometimes the aircraft won't start readily. And so it gives you a little bit more run time on the hydraulic motor so that hopefully you can get the engine started. So, but anyway, that's what they do. Okay. This is just a picture of the APU and the motor combination. So this is it's a small gas turbine, but again, there's a hydraulic motor that's attached to it. Once we motor the hydraulic motor, it'll start the APU. The APU then furnishes compressed air to start the main aircraft engine. Understand also too, there are other types of accumulators other than gas accumulators. You can have accumulators that use a spring in them instead. They have obvious advantages and disadvantages compared with gas type accumulators. With a spring accumulator, the spring is the pushing force in the accumulator. And what we can do is we can use the spring to force the fluid back out again. The disadvantage that I can give you with them, the disadvantage would be fatigue. If the spring begins to fatigue, obviously it's just like the gas charge being brought out of the accumulator, it's not going to work. There are also accumulators that are weighted. They're weighted accumulators. So what we just have is a dead weight on top of a piston, and again, it's the resisting force that allows fluid to resist entering into the accumulator. It's also the force that pushes the fluid back out of it too. So we can have a weighted type of accumulator or a spring type. Some of the Bell helicopters, I understand, used a spring type accumulator in their hydraulic system, but I can't remember where. Okay, a little bit on service valves. These are the valves we use to trap the gas pressure inside of the accumulator. They're used for other purposes as well. Sometimes these are used on shock struts for landing gear. If we've got a gas charged shock strut, these are the same type of valves that are used on them. resist the temptation to call these Schrader valves. Schrader is a company, it's a trade name, but these particular service valves are made by at least a couple of other different manufacturers. But they do trap gas pressure inside of it. There's three basic types of service valves that might be used with either shock struts or accumulators. The first type is called an AN812, and what I want you to remember about it is just a single piece type body assembly that they use for the valve or for the service valve. There is a device inside of it that provides a valve for a valve core. So if you take the dust cap off, you can see inside of it, screwed into it, you've got a valve core. The service range for this particular device is no more than about 1500 psi. And additionally, there's some specs for it regarding the torque on the body nut. Some of these service valves also have either a gasket that's mounted on the bottom of the valve next to that bears against the whatever you're trying to seal against, or there might be a groove that supports an O-ring that's there. It depends on the style of valve. But anyway, it's an EN812. The way that the valve operates, if you depress the valve core, the valve opens and the gas comes out. If you connect a gooseneck connection to the valve, depress the valve core, the gas will come into the valve. So it's pretty simple. So it's just a push type of valve that we have inside of it. There's a vent hole that's provided on the body of the valve that works as a safety feature. If someone doesn't know how the valve actually operates, the idea behind the vent hole is that if you were to unscrew the base nut and expose the vent hole, the gas would come out of the vent opening, hopefully before the entire valve becomes a missile as you unscrewed it too far. So the safety is really that vent hole that they provide in the valve. Okay, and again, there's a torque there for it as well. Also, too, I'll show you in a bit, on the very end of the valve core will be marked with an H. The H indicates high pressure. So anytime you see an H on a valve core, that's an indication for high pressure. There are other valve cores that will fit because they've got the same threading, but they'll last about a second. So be aware if you put an automotive type valve core into those things, they will fit, but they won't work. At least they won't work the intended way. So they'll probably blow themselves out. There's another type of service valve that's called a 6287. That particular one has got a base nut and a swivel nut, and it's also got a different type of high pressure valve core. This relies on two sealing features. It's got what is called a metal to metal seal, and it also has the sealing effect of the valve core. These were used in the 1950s or so on a lot of aircraft, and again, when they had pressures that had to be maintained above 1500, it provided for better leak resistance at higher pressures. So the service range of pressure goes to about 3000 psi. There are specified torque values for both the base nut and the swivel nut. And what you have to do in order to release pressure is first loosen the swivel nut in order to break the metal to metal seal, and then you can push it on the valve core in order to finally release the gas charge in the accumulator. And that's about all. Some of these have no safety feature on them whatsoever, so just be aware of that. There's one more type of valve that might be used for either accumulators or shock struts, and it's called the MS2889 valve. This one has got no valve core in it. What it has is a body nut and a swivel nut. When the body nut is tightened against the fitting, in order to release pressure, what you do is unscrew or turn the swivel nut in order to break the metal to metal seal, and the gas comes out. The safety feature that they provide on these, although they don't show it, is usually an interrupted thread. It serves the same function as the vent hole. If you were to mistakenly loosen the base nut, what you'll do is expose the open area of the interrupted threads, and then the gas will leak out of it. so it prevents it from kind of becoming a missile. Additionally, one other safety device of a valve is a roll pin. The roll pin is there to prevent complete disassembly of the components that make up the valve. If you, the roll pin is only free to traverse or move within an area that they kind of outline here. If you attempt to loosen the swivel nut too far, the roll pin prevents you from loosening the inner portion of the valve itself and prevents it from becoming a missile. So the service pressure for that particular one, it's about 5,000 PSI or so. This is probably the most widely used version of valves that you'll see, again, either for a shock strut or for an accumulator for servicing. So that's what you find, okay? Here's kind of a close-up view. Again, sometimes the 812 might be furnished with either a solid gasket, or sometimes there's a grooved area on the underside of it. You can see the vent hole here. The 6287 valve uses a different style of high-pressure valve core, but it's got a body nut and a swivel nut on it. Different sizes, by the way, too. And if you take a look at the MS valve, it's got a body nut and a swivel nut. If I remember right, this is, both of these, the body nut and the swivel nut are 3/4 inch. This one I think is 5/8 of 3/4, and I think this is 5/8 if I remember right for wrench sizes. I think I've got it written down somewhere here. So anyway, you can differentiate them by just kind of looking at them. They've got different sizes on them. If you have to replace one of these valves, you're going to replace it with the same one that was removed. So again, there's no interchange, even though the threads are generally all the same on the bottom. The problem is they're for different service ranges. So again, replace the valve with what's required. Okay, kind of a close-up view of these valves. And again, I wanted to get a view of the one style of high-pressure valve core. And one thing that identifies it as a high-pressure valve core is an H that's embossed on the head of the stem. Also, too, if you were to look up this AN spec, you'd find out also one further identifying feature is a copper-plated valve, what we call a swivel. But again, the FAA will ask you specifically about the H embossed on the head. You see an H that indicates high pressure, so obviously for that type of application. And here's a comparison. You see, if you look very carefully, there's an H embossed on the head. This one might be for low pressure, we don't know. But again, high pressure on the right. Okay, and all right. Now let's talk a little bit about servicing an accumulator. First of all, what does servicing mean? Servicing means this. It means verifying the correct gas, what's called the pre-charge of the accumulator, by both pressure and volume. So if somebody asks you to go service the accumulator, the first thing you want to do is know that you are not disassembling the accumulator. Disassembly infers either repair or overhaul. When we talk about servicing, servicing means servicing. You're checking and maybe possibly adding gas to the accumulator. We also have to be aware too, you're going to look at service instructions for a particular aircraft. So I can give you some rules of thumb in servicing, but again, look at the service instructions that you have for actually servicing an accumulator. There's a term called a gas pre-charge. And what that is the pushing force that's on the fluid. You're going to put that into the accumulator in order to be able to resist the fluid that would normally come into it. So this is the force that you are providing in the accumulator. The preferred gas is generally going to be nitrogen. And the reason that most manufacturers prefer nitrogen in this connotation is considered to be inert. It does not support combustion. So that's the reason why we use nitrogen. As an alternate, what might be specified in a service manual might be dry compressed air. The problem, though, with using compressed air is a couple that I can think of. Number one, compressed air contains oxygen by 21% by volume. So again, it's not really an ideal type of gas that might you possibly could use because it does help support combustion. And as you know, there are many hydraulic systems that still use mineral-based hydraulic fluids. So it's considered to be an alternate. Another reason they don't necessarily like compressed air is because it may be laden with water. If you're using compressed air from an unknown source, you may be unintentionally damaging the accumulator by introducing water to a metal component. So again, you can kind of think of what might result from something like that. So again, nitrogen probably the preferred gas.
How does nitrogen not hold water?
Generally doesn't support water. No, it doesn't harbor in it. Water or air will. Also, too, one other term. Anytime a person refers to an accumulator being flat, it means the same thing as a flat tire would mean. It means you've lost the gas charge. So a pilot reports that the accumulator has gone flat. It means probably what he's inferring is that you've lost the gas charge out of the accumulator by whatever means. Maybe the service valve was leaky, maybe the bladder was broken and the gas got into the fluid, whatever, but the accumulator has lost the gas charge. There's also a rule of thumb too regarding what manufacturers abide by when they install an accumulator. There will generally be enough pressure in that gas charge to operate any particular component in the circuit. Doesn't that make sense? Yes, of course. You wouldn't have an accumulator installed that wouldn't be able to operate an actuator when required. This is also a rule of thumb too. The pre-charge pressure is usually a fractional value of system pressure. Usually about 1/3 to 1/2 of whatever system pressure is. What does that mean? It means that if we've got maybe a regulated system pressure of maybe 1500 psi, the gas pressure that we would anticipate having in the accumulator, it might be somewhere between what and what? 1/3 would be 500. What would be a half? 750. So we would anticipate that. However, I've been fooled before. So again, we want to verify by looking in the service manual to verify what the actual pre-charge might be. But it's a rule of thumb that we sometimes abide by. Again, so read the aircraft maintenance manual and service manual for correct pre-charge pressure. Also too, this is important. Pressure is one thing, volume is something else. If there is trapped fluid in that accumulator, when you're trying to fill it with gas, the fluid is going to influence the amount of gas that's inside of that accumulator. Usually when accumulators are serviced, when they're properly serviced anyway, all the fluid has been forced out of it. So one thing that you do as you're charging the accumulator with gas, you may have to operate a selector valve in order to force any trapped fluid out of it back to the reservoir. So very important. This is important too. You're working with high pressure gas. Make sure that you guard your eyes when you do something like this. So wear safety glasses when you do it. And let's see, also, if you find out that the accumulator is going to have to be replaced for whatever reasons, you're obviously going to have to get the fluid out of it first. So if it's got a gas charge and it's got a fluid that's trapped into it, we'll operate a selector valve in order to vent the hydraulic fluid back to the reservoir, and then and only then will we open up the service valve to get rid of the gas charge. Does that make sense? Yes or no? I hope so, because there's an FAA test question that asks you what you do first, so there's a priority. So a hierarchy of order. If you have to remove an accumulator, you get rid of the fluid before you get rid of the gas. Okay? Okay. Typical normal indications. Well, let's go back to this picture and kind of take a quick look here. What time is it? It's close to 6. Would you like to take a break for 1/2 hour?
Yes.
Let us take a break for 1/2 hour, and then we'll cover a little bit on normal indications and servicing.